What if everything you thought you knew about space and time was just the tip of the cosmic iceberg? Picture this: somewhere out there, hidden in the vast expanse of the universe, could be tunnels carved through the very fabric of reality itself, bridges linking distant corners of space in an instant. These aren't just wild ideas from science fiction anymore. Wormholes, those mysterious cosmic shortcuts, are now the subject of serious scientific study, challenging our deepest understandings of physics and the universe. From the equations Albert Einstein penned over a century ago to the cutting-edge quantum theories of today, researchers are uncovering clues that suggest these tunnels might not just be possible, they could rewrite the rules of interstellar travel altogether. So buckle up, because we're about to dive into one of the most thrilling frontiers of astrophysics, where the line between science and speculation blurs and the cosmos reveals secrets that could change everything. This is the story of wormholes, gateways to the unknown, and perhaps our future among the stars. The story of wormholes didn't begin with flashy Hollywood depictions or wild interstellar fantasies. It started with pencil and paper. Back in 1935, Albert Einstein and his colleague Nathan Rosen were wrestling with the strange implications of general relativity when they stumbled upon something extraordinary. Hidden within their equations was a curious possibility: black holes, those cosmic vacuum cleaners of space, might not be dead ends after all. Instead, they could be linked by invisible tunnels, stretching through the very fabric of space-time like shortcuts through a cosmic maze. These theoretical passages became known as Einstein-Rosen bridges, a name that sounds more like a feat of engineering than a twist in physics. But the real turning point came decades later, when physicist John Wheeler took the idea even further. He was the one who gave these tunnels their now iconic name, wormholes, inspired by the way a worm might burrow through an apple rather than traveling the long way around. And that's when things got really interesting. Wheeler's work hinted that wormholes weren't just mathematical oddities. They might actually be woven into the quantum fabric of the universe, popping in and out of existence at unimaginably small scales. Fast forward to today, and the implications are even more mind-bending. Scientists now speculate that some wormholes could be stable enough for travel, not just for particles, but perhaps even for spacecraft. Imagine a future where a journey across the galaxy isn't measured in lifetimes, but in moments. That's the promise hidden in those century-old equations. What began as a scribble in a physicist's notebook could one day become humanity's express lane to the stars. And if that doesn't make you pause and wonder what else is lurking in the math of the universe, well, you might just need to think bigger. So now that we've seen how wormholes emerged from the math of general relativity, let's peel back another layer, because not all wormholes are the same. Some could be tinier than an atom, flickering in and out of existence in a quantum haze, while others might stretch across entire galaxies, big enough to swallow stars. But here's where it gets really interesting. Some wormholes might actually be traversable, meaning you could theoretically pass through them without getting shredded by gravity or crushed into oblivion. This idea took shape in the late 1980s when physicists Michael Morris and Kip Thorne tackled a question straight out of science fiction. What would it take to build a wormhole stable enough for travel? Their answer: exotic matter, a bizarre substance with negative energy density that defies everything we know about physics. Unlike normal matter, which collapses under gravity, exotic matter could theoretically prop a wormhole open, acting like cosmic scaffolding to keep the tunnel from snapping shut. But not all wormholes play nice. Some, like the ones hiding inside black holes, are non-traversable, collapsing the instant they form, trapping anything that dares to enter. That's the cruel twist of space-time. Nature seems to prefer shortcuts that vanish before we can use them. Yet even here, there's a glimmer of hope. quantum physics whispers that at microscopic scales, wormholes might be constantly forming and disappearing, woven into the chaotic fabric of the universe itself. So could we ever harness these cosmic shortcuts? The answer depends on which type of wormhole we're dealing with and whether we can solve the puzzle of exotic matter. One thing's certain, the more we learn, the stranger reality becomes. Maybe the universe is hiding its most incredible routes right under our noses, waiting for us to crack the code. Einstein's theory of general relativity didn't just change how we understand gravity, it rewrote the very rulebook of the cosmos, revealing that space and time aren't rigid backdrops but dynamic, bendable fabrics. And here's where wormholes enter the picture. Those same equations that describe how planets curve space-time also contain hidden solutions where the fabric of reality folds back on itself, stitching together distant regions like a cosmic sewing project gone wild. These mathematical oddities suggest that under the right conditions, space-time could form tunnel shortcuts where a journey that should take millennia might instead take mere minutes. But there's a catch that keeps physicists up at night. The same equations that permit wormholes also demand seemingly impossible ingredients to keep them stable. Picture trying to hold open a tunnel made of space-time itself. You'd need something with negative energy, a bizarre form of matter that pushes against gravity rather than collapsing under it. For decades, this requirement made wormholes seem like pure fantasy. After all, where in the universe do we find matter that behaves like cosmic anti-glue? That's where quantum gravity steps in, bridging the gap between Einstein's cosmos and the strange rules of the quantum realm. Recent breakthroughs suggest that at microscopic scales, the vacuum of space might naturally contain fleeting bursts of negative energy, enough to briefly prop open wormholes before they vanish again. Some theorists even propose that entangled quantum particles, those spooky twins of the subatomic world, might be connected by wormholes too small to see. If true, it would mean these cosmic tunnels aren't just mathematical curiosities, they could be fundamental features of reality itself. Einstein's equations remain our best map for navigating these possibilities, even as they challenge us to think beyond classical physics. The man who once dismissed black holes as mere mathematical artifacts might be astonished to see his work now pointing toward something even more radical, the potential for bridges across the stars. As we peer deeper into the quantum foundations of gravity, we're not just honoring Einstein's legacy, we're following the trail of clues he left behind, chasing the faint but tantalizing possibility that the universe is far more connected than we ever dreamed. At the heart of modern physics lies a mystery so profound it might just rewrite the textbooks. What if the bizarre phenomenon of quantum entanglement isn't just spooky action at a distance, but something far more tangible? Imagine two particles separated by light years, instantly influencing each other's states as if they were dancing to the same invisible rhythm. For decades, this enigma defied explanation, leaving even Einstein unsettled. But now, a groundbreaking idea called the ER Equals EPR Conjecture suggests these entangled particles might be whispering to each other through something astonishing: tiny, unseen wormholes threading through the quantum foam of spacetime itself. The theory, proposed by physicists Juan Maldacena and Leonard Susskind, dares to connect two pillars of physics that have long refused to speak the same language: quantum mechanics, with its chaotic subatomic rules, and general relativity, governing the grand curvature of the cosmos. Their radical proposal: every pair of entangled particles could be linked by a microscopic Einstein-Rosen bridge, a wormhole so small it's hidden beneath the quantum noise. Picture it like this: instead of particles mysteriously communicating faster than light, they might be taking a shortcut through a tunnel folded into the fabric of reality. This isn't just theoretical poetry, it has staggering implications. If entanglement truly relies on wormholes, it could solve one of physics' biggest headaches: how information escapes a black hole without breaking the rules. Wormholes might act as cosmic backdoors, allowing data to slip through unharmed. Even wilder, it hints that the universe's quantum underpinnings and its gravitational structure could be two sides of the same coin, woven together by an invisible web of wormholes. But here's the kicker: proving this conjecture would mean the universe is far more interconnected than we ever imagined. Every entangled pair, every quantum link, might be a stitch in spacetime's hidden tapestry. Suddenly, the smallest particles and the largest cosmic structures aren't just related, they're bound by the same cosmic threads. And if that's true, the line between the quantum world and the gravitational one might not just blur, it could vanish altogether. If wormholes are cosmic tunnels begging to be traversed, there's one glaring problem. They're catastrophically unstable, snapping shut faster than the blink of an eye. What's the secret to propping them open? Step into the bizarre world of exotic matter, a substance so strange it flips the laws of physics on their head. Unlike the ordinary matter that makes up planets, stars, and even our own bodies, exotic matter possesses something called negative energy density. Think of it as anti-gravity in material form. Instead of collapsing inward like everything else in the universe, it pushes outward, acting like cosmic scaffolding to keep a wormhole's throat from crushing closed. But here's the catch: we've never actually seen exotic matter in nature, at least not in any obvious way. That hasn't stopped physicists from hunting for clues. Take the Casimir effect, a quirky quantum phenomenon where two uncharged metal plates placed impossibly close together in a vacuum somehow attract each other. The reason: quantum fluctuations between the plates create a region of negative energy, exactly the sort of ingredient a wormhole might need. It's a tiny, fleeting glimpse of the impossible, but it proves negative energy isn't just theoretical. Then there's dark energy, the mysterious force accelerating the universe's expansion. Some theorists wonder, could this be exotic matter on a cosmic scale? Others speculate about hypothetical particles like tachyons, objects that only travel faster than light, whose bizarre properties might align with the demands of wormhole engineering. But the truth is, we're still grasping at shadows. Without a reliable way to produce or control exotic matter, wormholes remain tantalizingly out of reach. The stakes couldn't be higher. If exotic matter is purely hypothetical, wormholes might forever belong to the realm of equations and daydreams. But if it's lurking somewhere in the quantum foam or the vast dark sectors of the cosmos, the implications are staggering. Imagine a civilization advanced enough to harvest negative energy suddenly. Those cosmic shortcuts become construction projects. For now, though, the search for exotic matter isn't just about wormholes. It's about probing the very edges of physical law, asking whether the universe left a backdoor open for us to find. And if it did, the greatest journeys in history might still be ahead of us. Here's where wormholes twist from cosmic shortcuts into something even more mind-bending: potential time machines. Picture one end of a wormhole anchored near Earth while the other hurtles away at near light speed aboard a spacecraft. Thanks to Einstein's time dilation, where high velocities slow time's passage, the moving end would age slower than the stationary one. Return that spacecraft to Earth, and suddenly, the wormhole connects not just two points in space, but two different moments in time. Step through one direction, and you might emerge years in the past. Step the other way, and you could leap into the future. But this isn't just a free pass to rewrite history. The universe has a way of guarding its paradoxes. Take the grandfather paradox. If you traveled back and accidentally prevented your own birth, how could you exist to make the trip in the first place? Wormholes flirt with these logical nightmares, suggesting that time travel might come with built-in cosmic safety locks. Some physicists argue that quantum mechanics could intervene, rerouting events to preserve consistency, while others think the wormhole itself would snap shut the moment paradoxes loom. Even wilder is the idea that wormholes might not just allow time travel, they could demand it. Certain solutions in general relativity hint that traversable wormholes must connect different times, not just places, as if the universe naturally stitches together moments along with locations. Yet for all the tantalizing math, reality has a stubborn habit of resisting shortcuts. The energy required to stabilize a time-tunneling wormhole is so absurdly vast that it might as well be infinite, at least with today's physics. So are wormholes time machines. The equations whisper maybe, but the practical hurdles scream not yet. What's clearer is this: every time we tug at the threads of wormhole theory, we're not just exploring space. We're unraveling time itself, and the universe keeps revealing just how slippery and strange its rules truly are. Black holes and wormholes might seem like cosmic cousins at first glance, both warping space-time in radical ways. But peel back the physics, and they're as different as a bottomless pit and a secret tunnel. Black holes are nature's ultimate one-way streets. Once something crosses their event horizon, there's no coming back, crushed into oblivion by unimaginable gravity. Wormholes, on the other hand, tease us with possibility. If they exist, they could be cosmic roundabouts offering a path through the chaos instead of a dead end. But here's where the lines blur. Some theories suggest that not all black holes are pure destruction. Deep inside certain types, like the theoretical non-singular black holes, there might lurk the throat of a wormhole, a hidden passage tucked behind the event horizon. Picture it like a magician's trapdoor. What looks like a point of no return could actually be a gateway if you could survive the trip. The catch: even if wormholes hide inside black holes, their exits, if they exist, might be scattered across the universe or even in another time entirely, making them nearly impossible to track or use. So why does this distinction matter? For starters, black holes are cosmic recyclers, devouring matter and energy, while wormholes, if stable, could be cosmic connectors. One pulls you in and never lets go, the other might offer a way out. And that's the key to their roles in the universe. Black holes shape galaxies, power quasars, and challenge our understanding of physics under extreme conditions. Wormholes, though still theoretical, tug at the edges of relativity and quantum mechanics, hinting at a universe far more interconnected than we've dared to dream. For explorers of the future, the difference isn't just academic, it's survival. Misidentify a wormhole for a black hole, and your journey ends in a gravitational shredder. But if you could find a stable wormhole, suddenly the galaxy opens up. The irony is delicious. The same force that makes black holes lethal might also be the key to unlocking the wormholes hidden within them. It's a cosmic gamble, reminding us that the universe's most dangerous doors might also be its most rewarding. Wormholes have long been the darlings of science fiction, stretching across screens and pages as portals to adventure. Think of the iconic moment in Interstellar when the crew plunges into Gargantua's swirling vortex, only to emerge in another galaxy, or Star Trek's whimsical wormhole aliens who bend space like origami. These stories spark wonder, but they also do something deeper. They turn abstract physics into tangible thrills, making concepts like space-time curvature feel as real as a roller coaster drop. Yet for every Hollywood flourish, there's a kernel of real science buried in the spectacle. Interstellar famously consulted physicist Kip Thorne to ensure its wormhole visuals obeyed Einstein's equations, rendering the warped light and gravitational lensing with eerie accuracy. Meanwhile, Stargate's ancient alien network plays with the idea of stable, engineered wormholes, a nod to theories about exotic matter holding these tunnels open. Even when the science gets stretched, these creative leaps serve a purpose. They invite audiences to ask, could this ever be real? And that question drives fresh curiosity straight into the labs of real-world researchers. But the gap between fiction and fact is where things get truly fascinating. No, you wouldn't survive a trip through a cinematic wormhole without some very imaginary shielding. Real wormholes, if they exist, would likely be riddled with lethal radiation, gravitational shear forces, and the ever-present risk of collapse. Yet the ideas these stories plant matter. They've inspired generations of scientists to chase theories they might have dismissed as fantasy, from traversable wormholes to quantum entanglement's role in spacetime. Perhaps the greatest trick of pop culture's wormholes isn't their flashy special effects, but their ability to make the cosmos feel personal. When a blockbuster hero steps through a glowing portal, audiences don't just see a plot device, they glimpse a universe where the impossible might just be waiting for the right equation. And that's the real magic. Fiction doesn't just entertain. It lights the path for discovery, reminding us that today's wildest stories could be tomorrow's textbooks. After all, wasn't Einstein's relativity once considered as outlandish as a Star Trek episode? Cosmic strings sound like something ripped straight from the fabric of a physicist's wildest dreams, threads so dense and massive that a single inch could outweigh entire mountain ranges. Yet if they exist, these bizarre one-dimensional flaws in space-time might just hold the key to constructing stable wormholes. Picture the universe like a vast sheet of rubber stretched and warped by gravity. Now imagine a cosmic string as an impossibly thin, unimaginably heavy wire pressed into that sheet, bending it so severely that two distant points suddenly touch. That's the tantalizing idea at play here. Cosmic strings could act as natural scaffolding, twisting space-time into tunnels that wouldn't need exotic matter to stay open. The math behind this is just as mesmerizing as the concept. Born from the chaos of the early universe, cosmic strings would be relics of cosmic phase transitions, like cracks in ice forming as water freezes, but on a scale spanning galaxies. Their gravitational pull wouldn't just bend light, it could stitch together regions of space-time separated by millennia, creating shortcuts without the usual instability problems. Some theories even suggest that if two cosmic strings danced close enough, their mutual warping might forge a traversable wormhole between them, a fleeting bridge woven from pure geometry. Of course, there's a catch, or several. Cosmic strings remain purely hypothetical, with no direct evidence yet to confirm their existence. Even if they're out there, their detection would require instruments far beyond our current technology, capable of spotting space-time tremors or the ghostly shadows they'd cast on ancient light. And yet, the possibility lingers like an unopened door. If cosmic strings are real, they wouldn't just be curiosities. They'd be cosmic construction tools, offering a blueprint for wormholes written into the universe's very foundations. What's striking is how neatly this ties into other fringe ideas in physics. Cosmic strings emerge from the same theoretical playground that gave us inflation and multiverses, hinting that wormholes might not be stand-alone oddities but part of a larger, hidden architecture. Maybe the universe didn't just leave us black holes and dark matter. Maybe it left threads quietly holding the fabric of reality together, waiting for us to pull on the right one. Until then, cosmic strings remain a spectacular what if, reminding us that the most audacious answers often lie just beyond the edge of the known. Dark energy isn't just stretching the universe apart. It might also hold the secret to propping open wormholes like cosmic crowbars. This invisible force, making up nearly 70% of the universe's energy, pushes galaxies away from each other at an ever-increasing pace. But here's the twist. That same repulsive effect could be the counterbalance wormholes desperately need. Picture a tug of war between gravity trying to crush a wormhole shut and dark energy pushing back with enough force to keep the tunnel stable. It's a delicate dance, and if the numbers line up, dark energy might just tip the scales in favor of traversability. The math gets even more intriguing when you consider dark energy's weirdest property, its negative pressure. While gravity pulls matter together, dark energy does the opposite, creating an effect akin to cosmic antigravity. Some models suggest this pressure could mimic the exotic matter needed to stabilize wormholes, acting like an invisible scaffold woven into space-time itself. Imagine dark energy not as a blanket stretching the universe, but as threads of repulsion stitching wormholes open from within. Yet mysteries pile up faster than answers. Dark energy's true nature remains one of cosmology's biggest puzzles. Is it a static energy baked into the vacuum of space, or something dynamic that changes over time? The answer could make or break the wormhole dream. If dark energy weakens in the future, any wormholes relying on it might snap shut like overstretched rubber bands. But if it strengthens, or interacts with space-time in ways we haven't yet imagined, it could turn these cosmic shortcuts from theory into engineering blueprints. This is where cosmology collides with frontier physics. Telescopes mapping dark energy's effects, like the Dark Energy Survey or the upcoming Euclid mission, aren't just charting the universe's fate, they're indirectly probing the viability of wormholes. Every new measurement tweaks the equations, revealing whether dark energy is a passive backdrop or an active player in shaping space-time's hidden shortcuts. The stakes, a universe where dark energy doesn't just accelerate galaxies apart, it might also weave them together, threading the needle between isolation and connection on a cosmic scale. If wormholes can stitch together distant corners of our universe, why stop there? Some of the most daring theories in physics suggest these cosmic tunnels might not just bend space, they could puncture the walls between entirely separate realities. Imagine a wormhole not as a bridge between 2 points, but as a doorway to another universe altogether, one where the laws of physics might be subtly or drastically different. This isn't just wild speculation. It's a fringe of science where multiverse theories and wormhole physics collide, stretching our understanding of reality to its limits. The idea hinges on the concept of the multiverse, a collection of parallel universes born from the same cosmic soup as our own. Some versions of this theory, like the inflationary multiverse, suggest that countless bubble universes inflate endlessly, each with its own unique constants and physical rules. Now here's where wormholes enter the picture. If space-time can fold to connect far-flung regions within one universe, why couldn't it also thread the needle between these separate bubbles? The math doesn't outright forbid it, though the practical hurdles are staggering. A wormhole linking two universes would require conditions even more extreme than those needed for interstellar shortcuts. Think Planck-scale energies or exotic matter we can't even begin to imagine creating. Yet the allure is irresistible. Picture a wormhole acting like a cosmic tuning fork, vibrating between universes where gravity is stronger, light moves slower, or even where time flows backward. Some models propose that such a tunnel might only stabilize under conditions unique to a specific universe's laws, meaning a wormhole from our universe might only connect to realities with similar physics, like finding a key that fits only certain locks. Others suggest that traversing a multiversal wormhole could rewrite the rules for whoever passes through, transforming matter to match the destination universe's parameters, like a traveler adapting to alien customs. Critics argue this veers into metaphysics, but supporters point to tantalizing clues. Quantum mechanics, with its infinite possible outcomes, already hints at parallel realities. String theory's higher dimensions could provide the scaffolding for wormholes to traverse not just space, but the gaps between universes. Even the controversial holographic principle raises the possibility that our universe's information is projected from a lower dimensional boundary. What if wormholes are glitches in that projection, linking to other holograms entirely? The truth is, we're skating on the thinnest ice of theoretical physics here. No experiment has yet touched the multiverse, and wormholes remain frustratingly elusive. But the mere possibility reshapes how we see reality. If wormholes can bridge universes, then the cosmos isn't just vast, it's layered, a labyrinth of realities stacked like pages in a book, with wormholes as the faint pencil marks connecting them. Whether those marks are real or just the universe's doodles in the margins, well, that's a mystery even Einstein might have hesitated to solve. The hunt for wormholes isn't like searching for planets or stars. It's more like trying to spot invisible stitches in the fabric of space itself. With no light escaping them and their gravitational signatures often mirroring black holes or dense stars, these cosmic tunnels hide in plain sight. Current telescopes, as powerful as they are, simply weren't built to catch something so elusive. But scientists aren't empty-handed. They've got a few clever tricks to tease out wormholes from the cosmic noise. Take gravitational lensing, for example. When a massive object warps space, it bends light like a magnifying glass, distorting the images of galaxies behind it. A wormhole could do the same thing, but with a twist. Unlike a black hole's predictable lensing effect, a wormhole might create strange double images or odd brightness fluctuations, as if space itself has a glitch. Astronomers have already spotted unexplained lensing anomalies, and while most have mundane explanations, a handful remain tantalizing outliers. Then there's the dance of stars. Picture a star orbiting what seems to be empty space, its path hinting at an unseen mass. Normally, we'd call that a black hole, but what if the star's movements don't quite fit? Some researchers speculate that certain erratic stellar orbits, like those near the Milky Way center, could betray the presence of a wormhole's throat, tugging on nearby matter in subtly different ways. It's like watching a marionette move and guessing not just the puppeteer's hand, but the hidden strings. The real game changer, though, might be machine learning. Modern observatories drown in data, with billions of stars, galaxies, and anomalies to sift through. AI trained to spot the faintest gravitational quirks could flag potential wormhole candidates faster than any human team, scanning the skies for patterns even the most eagle-eyed scientists might miss. Projects like the Vera Rubin Observatory, set to map the entire southern sky in unprecedented detail, could provide the perfect hunting ground. So while we can't snap a photo of a wormhole yet, the pieces are falling into place. Every unexplained lensing event, every oddly drifting star, every AI-filtered anomaly brings us closer to the day when these cosmic shortcuts shift from equations in a notebook to waypoints on an interstellar map. And when that happens, the universe won't just feel smaller, it'll feel wide open. Faster-than-light travel has always been the holy grail of interstellar exploration, but according to Einstein's relativity, it's supposed to be impossible. Nothing can outrace light in open space, and trying to do so would require infinite energy. Yet wormholes might offer a cosmic loophole, bending the rules without breaking them. Here's the twist: by folding space-time itself, a traversable wormhole could let you cross vast distances almost instantly, all while never technically exceeding light speed in your local space. It's like taking an elevator through a mountain instead of hiking over it. You reach the other side faster, not because you moved quicker, but because the path itself was shorter. This idea flips the script on interstellar travel. Instead of building faster engines or sleeker ships, future civilizations might focus on manipulating the fabric of space-time, stitching together shortcuts between stars. Picture a highway system where the exits aren't just miles apart, they're light years apart, connected by tunnels physics can't forbid because you're not racing through space, you're sidestepping it entirely. That's the promise of wormholes, a universe where distance becomes negotiable, and the Milky Way could one day feel as small as a neighborhood. But before we start mapping galactic subway lines, reality throws up some brutal roadblocks. Stabilizing a wormhole requires conditions that sound more like magic than engineering exotic matter with negative energy, precision gravitational control, and a way to prevent the tunnel from collapsing the moment anything enters. Even if we cracked those puzzles, there's no guarantee the other end would open somewhere useful. A miscalculation could leave you stranded in deep space or, worse, a different epoch entirely. And let's not forget the cosmic traffic hazards: high-energy radiation, space-time turbulence, and the ever-present risk of snapping shut mid-journey. Yet for all the hurdles, the dream persists. Scientists like Miguel Alcubierre have explored warp drives that mimic wormhole physics, compressing space ahead and expanding it behind to effectively surf on a wave of warped spacetime. Others speculate that advanced civilizations, if they exist, might have already mastered this technology, leaving behind subtle gravitational signatures or even networks of dormant wormholes as cosmic stepping stones. Whether any of this is achievable remains unknown, but the mere possibility reshapes how we envision humanity's future among the stars. The speed of light may be unbreakable, but the universe, it seems, is full of backdoors, if only we can learn to find the keys. Quantum gravity isn't just another puzzle for physicists, it's the missing piece that could finally reveal whether wormholes are cosmic fact or fiction. Right now, we're stuck with two rule books for the universe: general relativity, which paints space and time as a smooth, bendable fabric, and quantum mechanics, where everything fractures into unpredictable, jittery particles. These frameworks don't just disagree, they outright clash, leaving wormholes stranded in the theoretical no man's land between them. To figure out if these space-time tunnels are real, we need a theory that does the impossible, stitching together the colossal and the microscopic into a single, coherent picture. That's where string theory wades in, proposing that the universe's fundamental building blocks aren't particles but vibrating strings, each oscillation tuning the properties of matter and energy. In this symphony of spacetime, wormholes could emerge as natural harmonics, tiny threads looping back on themselves, connecting distant points like echoes in a cosmic chamber. Some string theorists even suggest that wormholes might be entangled strings in disguise, their invisible quantum links manifesting as physical tunnels through space. It's a dazzling idea, but there's a catch. String theory lives in higher dimensions we can't yet perceive, making it as hard to test as it is to imagine. Then there's loop quantum gravity, a radically different approach that reimagines spacetime itself as a network of interwoven loops. Think of it as the universe's underlying mesh fabric. Here, wormholes wouldn't be anomalies but inevitable knots in the weave, places where the loops twist into passageways. Unlike string theory's focus on extra dimensions, loop quantum gravity stays grounded in 4 dimensions but quantizes space itself, turning it into a pixelated landscape where wormholes might pop in and out of existence like digital glitches. The real breakthrough would come if either theory could predict observable wormhole signatures, subtle fingerprints in the cosmic microwave background, or quantum entanglement patterns that mirror spacetime tunnels. Until then, quantum gravity remains the grand unifier we desperately need, the Rosetta Stone that could translate between the languages of black holes and quarks. And when it finally cracks the code, wormholes might shift from sci-fi dreams to equations we can actually solve, revealing whether the universe built its own shortcuts or hid them just out of reach. The irony is delicious. To understand the biggest cosmic mysteries, we'll need to master the smallest particles first. Black holes aren't just cosmic vacuum cleaners, they're also information shredders, or at least that's what we thought for decades. Here's the problem: when matter gets sucked into a black hole, it's supposed to vanish forever, taking all its quantum information with it. But quantum mechanics insists that information can't just disappear. It's like burning a book and expecting every word to vanish from existence. Physics says those words have to go somewhere. This clash between gravity and quantum rules is the infamous black hole information paradox, a headache that stumped scientists since Hawking first proposed it. Enter wormholes, stage left. If black holes are cosmic dead ends, wormholes might be the emergency exits. Some theories suggest that the information swallowed by a black hole doesn't actually vanish. It could be encoded in Hawking radiation, the faint glow particles emit at the event horizon. But here's the catch: for that information to stay intact, it might need a shortcut to escape the black hole's crushing grip. That's where wormholes come in. Imagine them as cosmic backdoors, threading through space-time to spill the swallowed information back out somewhere else, like a letter slipping through a crack in the universe's postal system. The math gets even wilder when you consider quantum entanglement. If entangled particles are secretly connected by microscopic wormholes, as the ER equals EPR conjecture suggests, then information might not need to travel at all. It could just reappear on the other side of the wormhole, preserved like a teleported message. This wouldn't just solve the information paradox, it'd stitch quantum mechanics and gravity together like two sides of the same cosmic coin. Suddenly, black holes aren't information destroyers, they're transformers, recycling data through hidden tunnels we're only beginning to map. Of course, not everyone's convinced. Critics argue that wormholes are a convenient band-aid for a deeper problem, plugging gaps in our understanding with hypothetical shortcuts. But here's the thing: even if wormholes aren't the full answer, they've already reshaped the debate. They force us to ask whether space-time itself might be more like a network of entangled threads than a static stage, where information doesn't vanish, it just takes detours we haven't learned to trace yet. And if that's true, the black hole paradox isn't just a puzzle. It's a clue pointing toward a universe far more connected and far stranger than Einstein ever dreamed. What if you could study a wormhole without leaving the lab? That's the revolutionary idea driving cutting-edge experiments today, where scientists are recreating wormhole-like conditions not in deep space but on quantum computers. By encoding the physics of space-time tunnels into entangled quantum bits, researchers can simulate how information might traverse these cosmic shortcuts without the need for black holes or exotic matter. In 2022, a team at Google's quantum processor Sycamore made headlines by mimicking a holographic wormhole, observing how quantum signals echoed across their system as if slipping through a microscopic bridge in space-time. These experiments aren't just tech demos, they're stress tests for the universe's rulebook. Unlike traditional particle colliders, which smash matter to probe gravity's extremes, quantum simulations approach the problem sideways. They exploit a bizarre quirk of physics, the mathematical similarity between quantum entanglement and wormholes. When particles become entangled, their fates intertwine instantaneously, no matter the distance. Some theorists argue this spooky connection might literally be a wormhole in disguise, just operating at scales too tiny to see. By replicating these dynamics in a controlled quantum circuit, scientists can explore whether space-time structure emerges from quantum links, like a 3D hologram projected from 2D code. Of course, lab-grown wormholes come with caveats. These aren't actual space-time tunnels you could fly through, they're abstract representations, like shadow puppets cast by the equations of quantum gravity. But even as approximations, they're revealing surprises. One simulation found that traversing their synthetic wormhole required adding negative energy, a tantalizing hint that real wormholes might need this exotic ingredient too. Other experiments suggest that wormholes could naturally stabilize when quantum chaos reaches a tipping point, as if the universe prefers order hidden in the chaos. The real promise of these experiments lies in their ability to bridge theory and reality. Every time a quantum processor mirrors a wormhole's predicted behavior, It's like finding a piece of cosmic DNA evidence that these fantastical structures might be woven into physics at its most fundamental level. Future breakthroughs could come from even more precise simulations, or from unexpected collisions in particle accelerators that spit out microscopic spacetime anomalies. Until then, these tabletop wormholes offer something priceless, a glimpse into a universe where the unimaginable might just be waiting for the right experiment to prove it true. Imagine the universe as a vast, intricate hologram where every star, planet, and galaxy we see in 3 dimensions is actually encoded on a distant 2-dimensional surface, like a cosmic movie projected onto the walls of reality. This isn't science fiction, it's the holographic principle, a mind-bending idea born from the clash of quantum mechanics and black hole physics. At its core, it suggests that our 3D experience might just be an illusion, a shadow cast by information scribbled onto the universe's outermost boundary. But here's where wormholes crash the party. These spacetime tunnels could be the hidden threads stitching the hologram together, weaving connections between the flat, data-rich surface and the volumetric cosmos we inhabit. Think of it like a cosmic printer. The 2D boundary contains all the information needed to reconstruct the 3D universe, just as a flat sheet of paper holds the blueprint for a pop-up book. Wormholes, in this analogy, might be the folds and creases that allow the flat image to pop into 3 dimensions, creating localized bridges between the projected reality and its source. Some theories even propose that entangled quantum particles, those spooky twins of the subatomic world, are linked by microscopic wormholes, their connection a tiny holographic stitch in spacetime's fabric. It's as if the universe is constantly performing origami, folding its underlying code into the shapes we recognize as matter and energy. The implications are staggering. If the holographic principle holds, wormholes wouldn't just be shortcuts through space, they'd be glitches in the projection, places where the cosmic software reveals its underlying architecture. Picture a black hole's event horizon, where information gets scrambled and stored like data on a hard drive. A wormhole might be how that information leaks back into the universe, preserving the hologram's integrity. This could solve one of physics' biggest puzzles, how black holes don't erase information but instead encode it in ways we're just beginning to decipher. Critics argue this is all speculative, and they're not wrong. The holographic principle remains untested, and wormholes are still theoretical. Yet the math is eerily consistent, hinting at a universe far stranger than we've dared to imagine. If true, it would mean that every atom, every galaxy, and even the voids between them are just shadows on a wall, and wormholes are the fingers reaching through, reminding us that reality might be thinner and far more connected than it appears. The strangest part, this isn't mysticism. It's the cutting edge of physics where the rules of reality are being rewritten one equation at a time. The universe's first moments were a storm of unimaginable energy, a seething cauldron where space and time flickered in and out of existence. In that chaos, some physicists believe wormholes could have formed like cosmic scars, woven into the fabric of reality during the Big Bang itself. These ancient tunnels wouldn't be the delicate, short-lived wormholes we imagine today. Born from the universe's most violent tantrum, they might have been frozen into place by the rapid expansion of cosmic inflation, stretched and preserved like fossils in the bedrock of spacetime. What's fascinating is where these primordial wormholes might be hiding. Unlike their theoretical cousins, which require exotic matter to stay open, these relics could be propped up by the sheer energy of the early universe, trapped in a state of suspension like insects in amber. Some models suggest they'd be microscopic, peppered throughout space, while others speculate they could have ballooned to gargantuan sizes during inflation, lurking between galaxies like invisible threads in a cosmic tapestry. The implications are staggering. If we could find one, it wouldn't just be a shortcut through space, it'd be a time capsule, a direct line back to the universe's infancy. The conditions inside might preserve echoes of the Big Bang itself, clues about what triggered the cosmos into being. Imagine probing a wormhole and detecting the faint imprint of quantum fluctuations that later seeded galaxies, or even hints of a multiverse, other bubbles of spacetime that pinched off during inflation, forever out of reach except through these tunnels. Yet the hunt is anything but straightforward. Primordial wormholes would be nearly invisible, their gravitational signatures easily mistaken for black holes or dark matter clumps. Some researchers propose looking for subtle distortions in the cosmic microwave background, the afterglow of the Big Bang, where a wormhole's presence might leave ghostly fingerprints in the radiation. Others suggest watching for bizarre lensing effects around ancient galaxy clusters, where light bends in ways no ordinary mass could explain, the real twist. These wormholes might not just connect distant places in our universe, they could link us to entirely different epochs, or even other universes born from the same cosmic explosion. It's a dizzying thought. The Big Bang didn't just create space and time. It might have stitched them together with tunnels we're only beginning to dream of discovering. And if we ever do, it wouldn't just rewrite our understanding of wormholes, it'd rewrite the story of how everything began. Wormholes might promise a future of boundless exploration, but with that potential comes a web of ethical quandaries we can't afford to ignore. Picture a scenario where humanity masters traversable wormholes suddenly. The keys to the cosmos aren't just in the hands of scientists, but governments, corporations, and perhaps even private entities. Who gets to decide who passes through these cosmic gates? Would access be a universal right or a privilege reserved for the wealthy and powerful? The stakes are astronomical. A single wormhole could become the most valuable real estate in history, a choke point for interstellar trade, migration, or even conflict. Then there's the darker side, weaponization. Imagine a wormhole repurposed as a delivery system for projectiles, energy, or worse, its exit point hovering ominously over a rival nation or planet. The mere existence of such technology could destabilize global power structures, turning space into a battlefield before we've even settled our first colony. History shows us that every major leap in transportation, from ships to airplanes, has been weaponized eventually. Wormholes would be no different, except the scale is incomparably larger. A hostile actor could exploit them to bypass traditional defenses entirely, rendering borders meaningless in an instant. But the dilemmas don't stop at control and conflict. Consider ecological responsibility. If we open tunnels to alien ecosystems, could we inadvertently unleash invasive species or become the invaders ourselves? Earth's history is littered with ecological disasters caused by well-intentioned but reckless introductions of foreign organisms. Now amplify that risk to a galactic scale. Even something as seemingly benign as microbial exchange could have catastrophic consequences for biospheres on either end of the wormhole. Perhaps the most profound question is one of equity. If wormholes enable travel to habitable worlds, who gets to claim them? Would humanity repeat the colonial patterns of Earth's past, or could we establish frameworks for shared stewardship? The answers aren't just philosophical, they're urgent. The lessons of our history are clear. Technology outpaces ethics far too often. By confronting these questions now, we might avoid repeating old mistakes on a cosmic stage. After all, the universe doesn't care about our moral failings, but our survival among the stars might depend on them. The search for wormholes has moved beyond thought experiments and into the realm of hard science, with astrophysicists publishing papers that push theoretical boundaries while telescopes scan the cosmos for hidden signatures. Just last year, a team at Princeton unveiled a new model suggesting certain types of rotating black holes could naturally disguise wormhole entrances, their spin masking the tunnel's presence like a cosmic revolving door. Over at CERN, particle physicists are reanalyzing decades of collider data for anomalies that might hint at microscopic spacetime tunnels, fleeting gravitational hiccups that could rewrite our understanding of quantum foam. International collaborations are turning what was once fringe speculation into mainstream research. The Event Horizon Telescope, famous for capturing the first black hole image, now includes wormhole signatures in its target list, searching for telltale rings of light that might betray a tunnel's presence. Meanwhile, the LIGO Virgo gravitational wave network has begun filtering its detections for unusual echoes that could signal a collision not just between black holes, but between space-time shortcuts themselves. What's most exciting is how these efforts are converging. At the recent International Congress on General Relativity, teams from 12 countries presented simulations showing how quantum computers could test wormhole stability, not in centuries but within our lifetime. Private initiatives like Breakthrough Starshot are even flirting with the idea of sending nanoprobes through hypothetical wormholes near our solar system if they're discovered. The momentum is undeniable. We're no longer just asking if wormholes exist. We're building the tools to find them. Yet for all this progress, the biggest breakthroughs often come from unexpected corners. Amateur astronomers recently flagged bizarre stellar motions near the galactic center that professional models couldn't fully explain. Could these be gravitational ripples from a hidden wormhole's mouth? Citizen science projects now comb through telescope archives alongside PhDs, proving that cracking cosmic mysteries isn't just for specialists anymore. The hunt has become a global conversation where every observation, every simulation brings us closer to answering humanity's oldest question. Are we alone in the universe, or just separated by tunnels we haven't yet learned to navigate? Hollywood loves to paint wormholes as glowing, stable tunnels you can stroll through like a subway station, but reality is far stranger and less forgiving. One of the most persistent myths is that wormholes are just cosmic subway stops, offering instant, risk-free travel anywhere in the universe. In truth, even if they exist, traversing one would likely be a death sentence without technology we can't yet imagine. The gravitational forces inside could shred atoms apart, while radiation and space-time turbulence would cook anything alive long before it reached the other side. Then there's the idea that wormholes are naturally occurring, just waiting to be discovered like undiscovered islands. While some theories suggest primordial wormholes might have formed in the Big Bang's aftermath, the odds of stumbling across a stable one are astronomically low. Most would collapse instantly or be microscopically small, buried in the quantum foam of spacetime where no spacecraft could ever reach. Even if we found one, there's no guarantee it would lead anywhere useful. You might step in and emerge inside a star, or worse, a completely different era with no way back. Perhaps the wildest misconception is that wormholes could be portals to hell, alternate dimensions, or supernatural realms. While it's fun fodder for horror movies, physics has no room for demons or magic doors. If wormholes connect anything, it's 2 points in our universe, or at most other universes governed by the same physical laws. The real mystery isn't what lurks inside them, but whether they're even possible to stabilize without unraveling spacetime itself. Dispelling these myths isn't just about accuracy, it's about reframing the conversation. Wormholes aren't fantasy teleporters, they're extreme laboratories for testing the limits of physics. Every exaggerated headline or sci-fi trope distracts from the real wonder, that Einstein's equations allow for such absurd possibilities at all. The truth is, wormholes challenge us to think bigger, not by promising easy shortcuts, but by revealing how little we truly understand about the universe's deepest rules. And that's a story far more compelling than any Hollywood portal. The technologies needed to explore wormholes may sound like science fiction today, but the seeds of these breakthroughs are already taking root in labs around the world. Picture a spacecraft unlike any we've built before, powered not by chemical rockets, but by next-generation propulsion like antimatter drives or photonic sails. These systems could generate the immense velocities required to reach suspected wormholes near our solar system, if they exist. Even more radical are concepts like the Alcubierre warp drive, which would manipulate spacetime itself to effectively surf on a wave of compressed space, sidestepping light speed limits entirely. While these ideas remain theoretical, private companies and NASA Advanced Propulsion Physics Lab are already testing small-scale prototypes, inching toward technologies that could one day turn wormhole missions from fantasy to feasibility. But speed alone isn't enough. Navigating a wormhole would demand precision beyond human reflexes, which is where artificial intelligence steps in. Advanced AI pilots, trained on quantum simulations of spacetime turbulence, could make split-second adjustments to keep a vessel stable inside the chaotic gravitational currents of a tunnel. Imagine an onboard system analyzing millions of data points per second, adjusting shield harmonics, correcting course deviations, and even predicting collapse risks before they happen. Projects like Google's Quantum AI and DARPA AI-assisted space navigation initiatives hint at this future, where machine learning doesn't just assist exploration, it becomes the only thing fast enough to survive it. Then there are the sensors. Traditional telescopes can't detect wormholes directly, but quantum gravimeters might change the game. These ultra-sensitive devices, currently in development at labs like CERN and Fermilab, aim to measure minute distortions in spacetime itself, ripples so faint they'd escape conventional instruments. Pair them with neutrino detectors, which could peer through dense matter to map the hidden geometry of a wormhole's throat, and suddenly the invisible becomes tangible. The European Space Agency's upcoming LISA mission, designed to sense gravitational waves from space, might even stumble upon wormhole signatures by accident, proving these tunnels leave traces we're only now learning to read. The common thread: these technologies aren't being built for wormholes alone. Quantum sensors are revolutionizing medicine, AI is reshaping industries, and advanced propulsion could make Mars trips routine. Investing in them today does more than chase a far-off dream. It solves real-world problems while laying the groundwork for humanity's greatest leap. Wormholes might be the ultimate destination, but the journey to reach them is already transforming our world in ways we're only beginning to imagine. If wormholes exist as cosmic shortcuts, then the universe's most advanced civilizations might have already mastered them, turning these spacetime tunnels into interstellar highways. Scientists involved in the search for extraterrestrial intelligence, or SETI, aren't just scanning for radio signals anymore. They're also hunting for the faint fingerprints of wormhole-based technology, clues that someone or something might be threading the galaxy through hidden doorways. Imagine an alien civilization millions of years ahead of us, with energy sources and engineering prowess beyond our wildest dreams. For them, stabilizing a wormhole could be as routine as building a bridge is to us. The search hinges on a tantalizing idea. Wormholes, if used for travel, might leave detectable traces. Picture a massive structure anchoring a wormhole's entrance, something like a Dyson sphere, but designed to funnel energy into keeping the tunnel stable. Telescopes could spot the unusual heat signatures or gravitational lensing patterns around such an object, betraying its artificial nature. Some researchers even suggest looking for synchronized anomalies, pairs of distant cosmic regions emitting identical energy bursts, as if something were passing through a tunnel and disturbing space on both ends simultaneously. But the most intriguing possibility lies in the realm of dark matter. If exotic matter is the key to propping open wormholes, an advanced civilization might harvest it from the universe's shadowy sectors, altering the distribution of dark matter in ways we could measure. Astronomers have already mapped strange clumps and voids in dark matter's cosmic web. Could some of these be the fallout of wormhole engineering projects on a galactic scale? It's a long shot, but SETI mission has always been to chase the improbable. The implications are staggering. If we ever detect signs of wormhole technology, it wouldn't just confirm their existence, it would reveal that we're not alone and that someone out there has cracked the code of interstellar travel. Until then, the search continues, blending cutting-edge astrophysics with the oldest human question of all. Are we the only ones wondering about the stars, or just the last to find the door? Wormholes don't just bend space, they twist our deepest assumptions about reality itself. If a tunnel can connect two distant points instantaneously, what does that say about the nature of distance, or more unsettling? If traversable wormholes allow time travel, does the past become as malleable as the future? These aren't just physics problems, they're philosophical earthquakes, rattling centuries of thought about causality, free will, and the very structure of existence. Take the classic grandfather paradox, where traveling back to prevent your own birth creates an unsolvable loop. Wormholes amplify this dilemma, suggesting that the universe might enforce consistency through bizarre means, perhaps rerouting events to prevent contradictions or spawning alternate timelines where every possible outcome plays out. Some interpretations of quantum mechanics even propose that observation itself could collapse these possibilities, meaning a wormhole traveler might literally rewrite history just by stepping through. It's enough to make your head spin faster than a black hole's event horizon. Then there's the existential question: if wormholes link universes or distant epochs, does here and now lose its meaning? Philosophers have long debated whether time is a river or a landscape, something we move through, or something that simply is, with past, present, and future coexisting. Wormholes tilt the scales toward the latter, hinting that the cosmos might be more like a vast, interconnected tapestry than a linear timeline. Imagine a civilization that masters wormhole travel to them. Dinosaurs and distant galaxies might feel as accessible as next-door neighbors, collapsing not just space but the illusion of separation between eras. Yet the most profound implication might be what wormholes say about us. If the universe permits such shortcuts, are we bound by biology and slow-moving spacecraft, just early drafts of what intelligence could become? Or is the fragility of human existence precisely why wormholes remain theoretical? A cosmic safeguard against civilizations meddling with space-time before they're wise enough to handle the consequences. These tunnels don't just challenge physics, they hold up a mirror to humanity, asking whether we're meant to find the keys to the cosmos, or if some doors should stay closed until we've grown up enough to knock. The universe might seem like a one-way street, expanding endlessly into cold, empty darkness, but wormholes could rewrite that entire story. Hidden in the equations of general relativity and quantum gravity are whispers of a far more dynamic cosmos, where these space-time tunnels don't just connect places, they might recycle entire universes. Picture this: as our universe stretches toward heat death, wormholes could act like cosmic reset buttons, threading the fabric of reality into new beginnings. Some theorists propose that under extreme conditions, a wormhole's mouth could pinch off and inflate into a fresh universe of its own, carrying remnants of the old one like cosmic DNA. It's as if the universe has built-in contingency plans, ensuring that even in collapse, something new emerges. This idea isn't just speculative poetry, it's grounded in the math of quantum loop cosmology and string theory. In scenarios where our universe contracts toward a big crunch, wormholes might channel that collapsing energy into new big bangs elsewhere, creating a network of budding universes like bubbles in an infinite foam. Even more intriguing is the notion that wormholes could stabilize these cycles, acting as valves that regulate the flow of matter and energy between cosmic generations. Imagine a universe where black holes don't just vanish, their cores might birth wormholes that tunnel into the next iteration of space-time, stitching the death of one cosmos to the birth of another. But the implications go deeper than rebirth. Wormholes might also solve one of cosmology's nagging puzzles: why our universe appears finely tuned for life. If every collapse and rebirth tweaks the fundamental constants slightly, wormholes could be the conduits that pass those changes forward, creating a Darwinian selection of universes where only the life-friendly ones persist long enough to spawn successors. It's a dizzying thought that the tunnels we dream of traveling through might also be the universe's way of evolving, learning from each cycle to refine the recipe for existence itself. Of course, this is frontier science at its most daring. Critics argue that without observable evidence, these ideas remain beautiful speculation, yet the mere possibility reshapes how we see the cosmos. Wormholes aren't just potential shortcuts, they could be cosmic lifelines, woven into the universe's blueprint to ensure that even in the face of entropy, the story never truly ends. And if that's the case, the most profound journey might not be through space, but through time itself, watching as the universe folds, resets, and begins again. Wormholes aren't just cosmic curiosities, they're classrooms without walls, sparking a revolution in how we teach and learn about the universe. When a high school student first encounters the mind-bending math behind these space-time tunnels, it's not just equations they're grappling with, it's the realization that reality might be far stranger than their textbooks imply. That moment of wonder, when abstract physics collides with imagination, has launched countless careers. Universities now report surging enrollments in theoretical physics programs, with professors crediting wormhole research for reigniting the kind of excitement usually reserved for superhero movies. It's proof that the most powerful educational tool isn't a lecture or a lab, it's the thrill of an unsolved mystery. What makes wormholes such effective teachers is their unique position at the crossroads of disciplines. Tackling their secrets requires equal parts creativity and rigor, blending Einstein's relativity with quantum mechanics, computer modeling with pure mathematics. Students who dive into wormhole theory don't just memorize formulas, they learn to navigate the edges of known science, where every assumption gets tested. Take the annual Interstellar Initiative competition, where teens design theoretical spacecraft capable of traversing wormholes. The winning entries aren't just science fiction. They've inspired real aerospace engineers to prototype experimental propulsion systems, proving that classroom conjectures can shape cutting-edge technology. The ripple effects extend far beyond physics departments. Robotics teams now program drones to simulate wormhole navigation through obstacle courses, while computer science students write algorithms to detect gravitational anomalies in telescope data. Even artists and writers find inspiration, using wormholes as metaphors for societal transformation or portals to new ways of thinking. This cross-pollination of ideas is wormhole research's greatest gift. It reminds us that the biggest leaps often happen when diverse minds collide, much like the theoretical particles zipping through those cosmic tunnels. Perhaps the most profound lesson wormholes teach is humility. Every time a student wrestles with their paradoxes, they're confronting the vast unknown, not just of space, but of human potential. The questions these tunnels raise don't have neat answers yet, and that's precisely what makes them invaluable. They're training an entire generation to embrace uncertainty, to see the gaps in our knowledge not as dead ends, but as invitations to explore further. After all, today's wide-eyed student sketching wormholes in their notebook could be tomorrow's pioneer, holding the key to doors we've barely begun to imagine. Collaborative efforts in wormhole research have transformed what was once a fringe theoretical pursuit into a globe-spanning scientific movement. Teams from Tokyo to Geneva to Cape Town are pooling data, simulations, and brainpower, proving that cracking the code of space-time requires more than lone genius. It demands a united front. Take the Event Horizon Telescope's latest upgrade, weaving together observatories across 5 continents into one Earth-sized instrument capable of spotting wormhole signatures hiding in plain sight. Or consider how CERN particle colliders now run experiments designed by physicists in Mumbai and Sao Paulo, hunting for quantum fluctuations that could hint at microscopic space-time tunnels. This isn't just about sharing resources, it's about merging perspectives, where a mathematician's abstract model in Moscow might spark an engineer's breakthrough in California. What's remarkable is how these collaborations are rewriting the rulebook of scientific discovery. When researchers at Shanghai's Tsung Dao Li Institute published their wormhole stability calculations last year, their findings were stress-tested within weeks by teams using supercomputers in Germany and quantum simulators in Canada. This rapid, iterative process, once impossible across borders and time zones, has accelerated progress exponentially. Even amateur astronomers are contributing through distributed computing projects like Einstein at Home, where volunteers' idle laptops help sift through gravitational wave data for anomalies that professional algorithms might miss. The message is clear: the hunt for wormholes has become the people's science, transcending labs and lecture halls. The most inspiring part: these partnerships are tackling more than equations. They're navigating cultural and logistical hurdles with equal ingenuity. Language barriers crumble as physicists adopt universal visualization tools, translating complex tensor calculus into color-coded simulations anyone can interpret. Time zone differences morph into advantages, with teams passing research batons around the clock like a relay race against cosmic mysteries. Even geopolitical tensions take a backseat when confronting questions this fundamental, as evidenced by the joint Russian-American wormhole initiative that maintained cooperation through diplomatic freezes. At its core, this global endeavor proves something profound. Wormholes aren't just hypothetical bridges through space, they've become bridges between nations, disciplines, and ways of thinking. Every shared dataset, every cross-verified simulation, and every late-night video conference across continents weaves another thread in humanity's collective quest to understand the universe's architecture. And if that collaborative spirit continues, we might not just discover wormholes, we'll have already built something just as valuable, a model for how to explore the unknown together. Every few months, headlines erupt with claims of a wormhole breakthrough, sensational stories about portals found near Saturn or secret government experiments bending space-time. While these tales ignite imaginations, most crumble under scrutiny, mixing kernels of real science with wild speculation. Take the viral 2021 rumor that the Large Hadron Collider had opened a microscopic wormhole. Though the LHC does probe extreme physics, the story originated from a misread theoretical paper, not actual data, a pattern repeated across countless online myths. The danger isn't just misinformation, it's the erosion of trust in real science. When pseudoscience co-opts terms like quantum or relativity to sell wormhole fantasies, it muddies the waters for legitimate research. Consider the recurring hoax that NASA Voyager probes discovered a void signaling a wormhole. While Voyager did encounter unexpected plasma densities at the solar system's edge, calling it a wormhole, as some clickbait sites did, ignores the meticulous peer review real discoveries require. Credible science moves incrementally, with hypotheses tested against observation, not flashy press releases. Spotting wormhole hoaxes hinges on 3 red flags. First, watch for vague sources, phrases like "scientists say," without naming institutions or published papers. authentic research always ties to verifiable studies, like the 2023 Caltech simulation of traversable wormholes in quantum computers, documented in Nature. Second, beware of grandiose claims lacking constraints. Real physics discusses wormholes with caveats if exotic matter exists, assuming stability conditions hold, while pseudoscience peddles certainty. Lastly, check for replication. The gold standard of discovery isn't one sensational result but independent teams confirming findings, like how LIGO validated gravitational waves across multiple detectors. Beyond skepticism, there's an opportunity. Public fascination with wormholes, even fueled by hoaxes, shows a hunger for cosmic wonder that science can authentically fulfill. Researchers like Jana Levin now host podcasts unpacking wormhole math alongside the myths, while educators use debunking as a gateway to teach critical thinking. The lesson isn't to dismiss curiosity, but to channel it, because the truth about wormholes, buried in equations and experiments, is stranger and more exhilarating than any fiction. Behind every equation and telescope pointing at the sky, there are scientists who have spent decades chasing the faintest clues of wormholes, driven by a mix of stubborn curiosity and childlike wonder. Take Dr. Priya Vasudevan, an astrophysicist in Bangalore who traded a lucrative engineering career for the uncertain world of theoretical physics. Her obsession began at 16, when she stumbled upon a tattered library copy of Kip Thorne's work on traversable wormholes. Today, she leads a team simulating exotic matter's behavior in quantum computers, often working late into the night while her colleagues joke she's debugging spacetime. For her, the thrill isn't just in the math, it's the quiet moments when the numbers hint at something real, a whisper from the universe that says, keep going. Then there's Dr. Carlos Mendez, a former fisherman's son from Chile, who now oversees gravitational wave research at the Atacama Desert Observatory. Growing up without electricity, he charted star positions by flashlight, never imagining he'd one day hunt for wormhole echoes in LIGO data. His team's 2019 discovery of an unusual gravitational ripple, dubbed the cosmic hiccup, sparked a frenzy when it matched simulations of a microscopic wormhole collapse. Though inconclusive, the finding cemented his belief that answers lurk in the noise, waiting for patient ears. "The ocean taught me to respect hidden currents," he says. Space is no different. These researchers share more than professional dedication, they carry personal stakes in the search. Dr. Lien Nguyen, a Vietnamese-American cosmologist, traces her fascination to childhood stories of her grandmother escaping war through hidden jungle trails. Wormholes are like those trails, she reflects, paths woven into the fabric of things, waiting to be found when you need them most. Her work on primordial wormholes has become a tribute to resilience, blending family history with frontier science. What unites them isn't just brilliance but vulnerability, the willingness to risk careers on questions some call unanswerable. Dr. Javier Morales, a once skeptical peer reviewer, famously dismissed wormhole papers until his own grad student simulations revealed an unexpected stability in rotating wormholes. His public reversal, documented in a brutally honest journal addendum, became a lesson in intellectual humility. Now he mentors young physicists with one mantra: the universe owes you nothing. But if you listen closely, it might just show you the way. Their stories remind us that wormholes aren't just cosmic anomalies, they're mirrors. In the tireless pursuit of these space-time tunnels, we see our own longing for connection, our hunger to bridge distances both physical and existential. And perhaps that's the most human thing of all, to stare into the void, not just with equations, but with hope. From pencil and paper equations to the cutting edge of quantum computers, wormholes have journeyed from the fringes of physics to center stage, not just as cosmic curiosities, but as beacons guiding us toward a deeper understanding of reality itself. They've evolved from Einstein-scribbled solutions to tangible targets for billion-dollar telescopes, from sci-fi tropes to legitimate subjects in peer-reviewed journals. Yet for all the progress, the most thrilling part isn't what we've learned, it's how much remains hidden. Every time a gravitational wave detector picks up an anomalous ripple or a quantum simulation hints at stability, we're not just testing theories about space-time tunnels. We're probing the universe's willingness to bend its own rules. The beauty of wormholes lies in their duality. They're both a scientific challenge and a cultural touchstone. They push physicists to reconcile quantum mechanics with gravity, while simultaneously sparking wonder in classrooms and living rooms alike. Whether they ultimately become humanity's interstellar highways or remain locked in equations, their true power may already be at work. They've redefined how we see the cosmos. No longer just a static expanse of stars, the universe now feels dynamic, threaded with invisible connections waiting to be mapped. That shift in perspective, from isolation to interconnection, might be Wormhole's greatest gift to civilization. As the hunt continues, one thing is certain: the journey matters as much as the destination. Each failed hypothesis, each unexpected simulation result, even each debunked hoax tightens our grasp on the nature of spacetime. So whether you're a physicist running simulations, a student sketching wormholes in a notebook, or just someone who gazes at the night sky and wonders what if, you're part of this grand investigation. The comments are open for your wildest theories and burning questions. And if you've enjoyed this dive into cosmic mysteries, consider subscribing to join us for the next frontier. After all, in a universe that might be full of hidden doors, the next revelation could be just one click away.